Hello, welcome back to Watchpoint. I'm Greg, and today we're going to look at Helgrind, kind of the equivalent of Thread Sanitizer, but in a Helgrind world. And we'll compare the two a bit, see some differences and similarities. So remember this, our cat race, simplest race we could imagine. So just like before with Thread Sanitizer, gcc minus g race.c minus pthread, and then we run it through Helgrind. But we're going to tell Helgrind which tool to use. By the way, you can tab complete, tab, and we see lots of different tools that can be used. We're going to run Helgrind, which is the kind of data race detector. And it works kind of in the same way as Thread. I mean, it predates Thread Sanitizer, so perhaps I should say Thread Sanitizer works in a very similar way to Helgrind. Unlike Thread Sanitizer, which is of course basically essentially a compiler feature, this runs your vanilla binary without any modification. So here we go. All right, let's see what it told us. So it says we're running in Helgrind. We expected that. Thread number 1, so thread announcement. So it's saying here's a thread, another thread announcement. The thread is created, fine. Look, here's where it's created from. Maybe that's interesting. Now this certainly is starting to look interesting. So we've got a possible data race. So data race is here at race.c line 19 because this conflicts with an earlier write. So race.c19 is reading from something that was written by another thread at another time, and there's no locking or anything in between. And so Helgrind says that looks a bit dodgy, and it gives us a bit of some clues, some little bit of clues here, so we can run with the procs or none to gain increased speed across the juicer. Let's have a look at some of the options that are available. So if you recall from Thread Sanitizer, we passed options in via an environment variable because you kind of have to, right? Because there's nothing else you run. It's just this compiler feature, whereas Helgrind is a separate tool. So we pass things in through the command line. So let's have a look. Some of the options we've got here. So it's free is right. I think this is probably quite useful. So when you free some memory or delete it in C++, if you've written to it before you free it, it will say, well, that's probably a race, right? How come I wrote that and freed it without anybody reading from it? Track lock ordering. So it does this. Now, Thread Sanitizer also tracks lock ordering, and we'll look at this in just a moment. It's another kind of race, not a data race. So actually, both Thread Sanitizer and Helgrind are a bit more than data race. Data race detectors, like at their core, but they kind of do a bunch of other stuff as well. We saw about we saw earlier about Thread Sanitizer's detection of signal handlers which made calls to functions which were not async signal safe. This is the thing that goes in the output history level, so we can kind of dial it down and up a bit, about to go slower but more thorough versus faster but more things are going to fall through. It's going to let less thorough checking. Essentially, at the full level, what it's doing is every single write to memory and every single read to memory is intercepted, and it will check for have two threads or more than one thread access this in a way that look kind of racy. And what we generally mean by that, if I've got a bunch of threads reading from some memory but nobody's writing, that's probably race free. If I've got a bunch of threads, some threads reading and at least one thread writing, and there's no interleaving lock, that's an indication of a race. It might not be a race, of course. We can write lock-free data structures, or maybe we don't care. And I'll show you an example about this just now. And this is and we'll also see one of the differences actually between Helgrind and Thread Sanitizer that may not be immediately obvious, but is pretty important. So that was the simplest race we could imagine, and simplest invocation of Helgrind, all very simple. Let's do something a little bit more funky here. So I've got a program that I've called threads.c. I'll show you what it does. Easier just to run it than show you the code, I think. And so it spins up 4 worker threads, and they're all just running away, and they're just incrementing this sort of ASCII character and printing it out to the screen independently. So, okay. Now I can run this with Thread Sanitizer. Actually, but let me just show you the code very quickly, because this is an example of some code that is actually a bit racy, because each thread is incrementing this spinners. Got this spinners thing, if you notice, look, starts off AAA, and then each thread, based on its index, is going to increment that those characters. So that sort of word of memory is being updated. Interestingly enough, each character, each 8-bit byte is being updated independently. So I would say actually that's not racy. But let's have a look. Let's have a look at what Thread Sanitizer and Helgrind make of that. So I just already compiled it. Let's compile it with Thread Sanitizer first of all. So if you recall, we do it. It's a compiler feature, like I said. So f sanitize equals thread. Again, all tab completes. And so we run it. And yeah, okay, so it's actually saying it thinks there's a data race here at line 19. Well, compared, and there's something at line 32. So let's have a look. What's it complaining about here? So actually, I think maybe it's right. Maybe there is a bit of a race because this thread is writing into this spinners array, and the main thread. No, not the main thread, but this thread. Each thread is outputting the spinners array sort of on top of each other. So yeah, that is gonna be a bit racy. It's only outputting sort of quasi-random characters, so you know it's not array. It's kind of that is kind of by program design, but it is kind of a data race. And actually, in the later versions of C++, it declares that any data race is actually undefined behavior. So that suddenly that program is technically incorrect, but it does what I wanted to do here. So if we run it, just run it once more, watch it go. So you can see it runs basically the same as it did originally. It's going to be running slower because Thread Sanitizer does introduce slowdown, but not sort of noticeably so, right? Now let's run it with recompile it without Thread Sanitizer. And we're going to run it through Helgrind, run it through Helgrind again, and let's watch this go. Now look at that. So it's found some races again, fine, but you can see actually. So Helgrind will run one thread at a time, and it kind of does its own scheduling between threads. And you can you can see it. It's observable, right? You can see one thread at a time running here. So clearly that's going to change your program behavior in some ways, at least slow it down. The scheduling is actually preemptive, and it is perfectly good for finding race conditions. And there are tools that do this, right? I mean, my own company undo.io's live recorder will do a similar kind of thing actually. And people often say, well, hang on, if you're serializing all the threads and you're only running one thread at a time, surely that's going to make all the race conditions go away. And actually, that's kind of the point of this, like Helgrind, like live recorder. It doesn't. It is more like if you from the good old days when we'd run multi-threaded program on a single core system, you still get race conditions, right? Because it's time sliced effectively. And same thing's going on here. So, and you can see it. I mean, we've got evidence here. It's detecting the races perfectly well, but it is only running one thread at a time. So clearly that is going to have an impact on how long, how quickly the program can run, how much throughput you're going to get, or how long it takes to run. But we all know how long it takes to find race conditions. So if the trade-off is, well, my program's going to run a little bit slower, but it's just going to tell me where the races are, that's going to save you a lot of time most times versus, your program runs at full speed, but now you've got to kind of run it a million times with all different printfs and whatever other mechanism you're doing to try and track down those races. So a good trade-off, but an important kind of characteristic to be aware of. I am also, let's also look at locks. Both Thread Sanitizer and Helgrind do the same thing here with respect to lock ordering. So again, this is not a data race, but it is a race condition. We've got things that the program will be non-deterministic based on which threads grab which locks in which order. So the kind of useful rule of thumb, if I've got a multi-threaded program taking locks, then, I mean, if I'm taking locks, it probably is multi-threaded, but you know what I mean. And if I've got more than one lock being held at the same time, if I take lock A and lock B, then I always want to take those in the same order, right? So if lock B is sometimes taken when lock A is held, then I'd better not try and take lock A when lock B is held, because that's likely to lead to deadlock, okay? Because one thread has got A, wants B, the other thread has got B, wants A, neither of those threads are going to make any progress, right? And it's relatively easy for things like Helgrind and address sanitizer and thread sanitizer, sorry, to catch these. So let's have a look at how that works. So I just tried. I thought it'd be interesting to try the simplest. I mean, this is not a deadlock because there's only one thread. So this actually is a false positive. There's no chance for deadlock because I know that I'm taking lock A and then lock B and then here I'm taking B and then A, but it's all within one thread. I'm not going to be doing those concurrently. Never going to be a deadlock. But suffice to say, it's probably worth thinking about at least, and it's good that the tools will warn you about this. So let's run that through thread. Let's run it through Helgrind first of all. Okay, and look, it's saying, okay, thread 1 is program's root thread, and there's a lock order violation. So this lock is taken before this lock, but the order acquisition was seen elsewhere in the other way around. Okay, so technically not a potential deadlock, but you can see how how that false positive was generated. Let's do the same thing for thread sanitizer. So sanitize equals thread locks minus LP thread, and let's run that. And you can see it's basically the same. It's a little bit more, maybe this is a bit more readable, this output, a little bit more concise, but maybe a little less information, but basically the same thing. Look, there's a cycle in the lock order graph. So it's saying thread sanitizer here is sort of labeling these locks. So M1 is the first mutex, M0 is the first mutex, M1 is the second mutex. Given it's a compiler feature, it could have just told me like the variable name for those mutexes, I guess. But anyway, it didn't. And it's saying that there's M1 is acquired. M1 is acquired here while holding M0, and M0 is acquired here while holding M1, and so that looks block order inversion, and it bails. So look, we can get some more information. So let's try that. So if we remember, Helgrind gave us a bit more information, but maybe if I do this, I've never actually done this before, so I'm going to see what happens. Not a whole lot more information actually, but that was just interesting to see. I just thought I'd try that there. So there you are, Helgrind and thread sanitizer, kind of pretty much doing the same job. Different trade-offs. Can you recompile your code? Do you want to recompile your code? Do you really want all the threads to run at one time? And do you really, or at least, and rather, do you really care about how fast the thing is going to run? If you really care about how fast it's going to run and you can recompile it, address sanitizer might be a win for you. If runtime execution is less important, or you don't want to or cannot recompile the code, then Helgrind is your friend. Right, that's it. Thank you for listening. See you next time.